there's no technician from Schism, so online people, can you hear me?
Yes.
Yeah.
Yes,
Great.
we can.
And you also see the slides, right? So
yes.
Screen sharing is okay. Then we are set. Yeah. So happy to see so many here and so many in the chat on the remote side. Let me briefly introduce myself. My name is Matthias Möller, one of the co-organizers of this together with Steffi, and also one of the lecturers, as you see. Otherwise, I wouldn't be standing here. And well, what I will be talking about, variation autoencoders, as everyone now said. Well, I have 1 or 2 slides on that, so to dampen your expectation. But no, I will discuss them and more in general. So about machine learning, specifically about physics-informed machine learning in design optimization. And yeah, a few words about myself. I'm a associate professor in Delft, TU Delft, in the numerical analysis group. That means I'm a mathematician by training, which also means I'm not showing too fancy, let's say, high-end applications, but I really start very low level to explain you how, or try to explain you how all these things work. And then sometimes with applications we have done together with industry partners, and also sometimes just, let's say, ideas of how we think it could be applied in the future. So that comes more or less to the end of the lectures. Yeah, so research interests, I should switch my hands and go to the presenter. Yeah, so of course, design, analysis and optimizations with isogeometric analysis. So I warn you, I also come from the finite element years. So I grew up with finite elements, unstructured finite elements, and then over several years, I more and more moved to IGA. But I'm not telling you IGA is the better FEA. I try to tell it like IGA is just the natural generalization of FEA. Yeah, and in the second part, I try to convince you that FEA, finite elements, can also be interpreted as lowest order IGA. Yeah, I just want to make this clear that kind of these are not two opposing things, but the one can be seen as a natural generalization of the other. Then, of course, scientific machine learning, yeah, and then more specifically physics-informed machine learning. So I'm, let's say, to be honest, 80% of the time I'm really the analysis guy. That means whatever we did with FEA or IGA, we are not trying to do in a different way with physics-informed machine learning. And a third thing, which at least this part seems related, high performance computing, and since a couple of years also quantum assisted computing. Story there is I like, let's say, non-conventional hardware. So GPUs were non-conventional some 10 years back. FPGAs are still unconventional. Quantum computers are maybe the most unconventional, most hyped computers at the moment. And well, we try to, or I with my group, you see here at least half of the group, try to explore, okay, can we use this soon or not so soon to come compute technology meaningfully for design, analysis, and optimization? Yeah, I'm not talking about that. I just wanted to let you know, kind of this is the split of my research group at the moment. Half of them, let's say, in the classical IGA SciML part, half of them on quantum. And so once in a while, I will talk about software projects. The 3 we are working on, or basically setting up, are GISMO, so geometry plus simulation modules. That's a bigger collaboration with INRIA, with Linz, with Florence, and with other universities. IGA-NETS is, yeah, a third part of the presentation, and LibCat is some quantum-related thing. By the way, if you have questions here or in the chat, just interrupt me, and even better, I try to make it interactive. So in the second part, I have something where I ask you questions. So be prepared, or escape before the break. Yeah. So talking about parts, I have these 5 parts. I structured it a little bit physics-informed machine learning, and this is really starting at the basics, explaining all the, let's say, ingredients up to how does a variational autoencoder work. Then second part, geometric modeling with splines. And this is also set up as a kind of tutorial. Really, what are the basic things you need to know about splines, up to how do you evaluate them most efficiently. Yeah, because, and here the circle closes, if you want to use splines in a training process, better don't use Cox de Boer. It is error prone and slow and everything but efficient. And we will talk about this. And even if you say, I don't care about, let's say, IGA, and I don't care about SciML, I just want a good, let's say, spline forward evaluator, you will get some, I hope you will get some useful information out of that. Yeah, then intro to IGA. This is not to sell you and to convert you to IGA evangelists, but this is kind of the theoretical underpinning of what we did in IGA nets. Yeah, then the IGA nets, and then finally something. Can I make this disappear? Okay. Caustic design. Anyone has an idea what caustic design is? Well, I just have two hands, so I have to put down the micro for a second, or maybe put it here. You can see this. So for those in the online, I just took a bottle of water and then let light shine through it, and then some patterns were here visible on the blackboard. These are caustics. You also have this if you have a swimming pool and sun is going through the water. You see these caustic things. You also see it if you have shallow water. At sunny days, you see on the ground this. That's not too useful, but there are some people who say, well, if we can kind of shape these patterns, and that is then not caustic, but caustic design, then we can make something out of it. At the moment, prominent example, if you have sports cars above, let's say, the 80K price, then if you open the door, you see, of course, the brand being projected on the ground and some other fancy ribbons or so. This is done with, you have very small LEDs and lenses, and these, let's say, this logo and the font or the writing on the street, this is done with caustic designs. Yeah, and well, we are not working with one of these high-price car manufacturers, unfortunately. So have to buy my car myself, but we work on design methods for that. Okay, let's start with part one, physics-informed machine learning, and 4 blocks, or sections. First, the terminology. Then I want to talk you through the 101 of machine learning. So really starting at what is an activation function, what's a neuron, but then very quickly also going to how does forward and backwards algorithmic differentiation work. So all the things that we see as magically functioning, but as a mathematician, I like magic, but I even more like to understand what goes on underneath. Then moving on to the physics-informed neural networks, call them PINs. I think you have heard about PINs. It's kind of impossible to not hear because Google Scholar basically every day has a new PIN paper if you subscribe to the right or wrong channels. And then the extension of that deep operator neural networks. And I hope to finish with all of this before Paris Perdikaris is talking this afternoon, because he will focus very intensively on the deep O-nets. Okay, terminology. This might sound silly, but very often people use, either because they don't know or they don't care, all these terms interchangeable. AI, ML, DL, SciML. And every one of us has some, let's say, idea what it is and some association. For example, we think about this AlphaGo winning against the world's best Go player, autonomous driving, ChatGPT, in whatever form, in the form of Copilot, in the form of Word is suggesting you how to write your proposal before you make up the sentences, fake images or deep fake images. And what I want to do in the next 5 minutes is kind of give a structure of what these terms are, and then how does physics-informed ML fit into that. So I see it like this. Yeah? AI is a superset of ML, is a superset of DL, and in general they are all statistical modeling approaches. Very often they kick out every pre-knowledge. Yeah, basically 500 years of physics knowledge are dumped, and we all base it on statistical modeling. Yeah, and it is helpful. Yeah, I don't want to be negative about this, because it very often allows you to discover empirically a new information, a new knowledge from big data. Yeah, so if the data is too large to be, let's say, analyzed manually, then these statistical modeling approaches can do it for you. Yeah, they are not actually understanding it, but they have a kind of better way to correlate data. And also something, I think Sebastian already mentioned that nowadays everything is called learning. Yeah, so linear regression or singular value decomposition or POD, which used to be around for, I don't know, 20, 30 years, some of them. Now they get a second life as learning methods. Yeah, so be careful whenever someone tells you, I have a new learning method, it could just be linear regression in a new clothes. But of course, this is kind of the baby steps, and you can go all the way to large language models that would be ChatGPT, Copilot, etc., or the other big hype, text-to-image, stable diffusion. Not sure, ever tried stable diffusion? You kind of describe which scene you want to see, and then you get an artificially created image, which very often looks quite realistic, I must say. Okay, I try to, let's say, make this subset diagram a little bit more tractable. François Collet, so he's the creator of Keras. Keras is one of the, let's say, widely or more widely used machine learning packages, says AI is the effort to automate intellectual tasks that are normally performed by humans. Yeah. Point is, he's not talking about learning at all. Yeah, he's just talking about to automate intellectual tasks. And as an example, and I agree, it's a kind of extreme example, you could think of a packing machine, which is rule-based or label-based. This thing is anything but intelligent. This thing does anything but learn. Just a programmer said, maybe after, I don't know, 80 grams of whatever this is, stop, seal it, cut it, next bin or next pocket. Yeah. So AI, in this definition, has not yet anything to do with learning. That comes if we go to ML, machine learning, there the L comes in. Another one, Arthur Samuel, an ML pioneer, defines it as the field of study that gives computers the ability to learn without being explicitly programmed. Yeah, so AI can be explicitly rule-based programmed, ML not. Yeah, so this self-learning or this learning capability comes in here. For example, if we have a waste sorting machine, unfortunately, your trash doesn't have a nice label. I'm this, I'm that, I'm that. Yeah, so a waste sorting machine could not scan labels and decide where to put it. Yeah, so this, and also we can't program all the possible, say, states of a destroyed plastic bottle. Yeah, this machine has to be self-learning or has to be able to learn in some sense. Yeah, and then DL. Yeah, there is not really a clear separation. You could say ML at big scale. Yeah, so if the networks become deeper, and especially this is let's say targeting a deep ANNs, artificial neural networks, then people talk about DL. Yeah, and I would say the border between ML and DL is a little bit, shady, a little bit vague, depending on who speaks about it and also to whom you want to sell it. ML sounds maybe less sexy than DL. Okay, now the question is, where comes physics into play? Yeah, let's leave all the AML, DL things for a moment, and let's just look at physics-based models. Yeah, Navier-Stokes equations, Poisson equations, structural analysis, Kirchhoff-Love shell, all that. These are physical laws, that have a very clear mathematical formulation, and they are derived, yeah, from observational studies and experiments. Yeah, and nowadays, or let's say in the old days, up to nowadays, were solved by numerical methods like finite elements, finite volumes, as Gianluigi was pointing out and Sebastian was pointing out. And actually, the kind of intersection of the two, I would consider, and I think most people agree, as SciML. Yeah, so to keep the, let's say, good old physics models that have been approved over decades with the capability of DL. And the point I want to make here, I think SciML as a, let's say, as a brand or as a name was, yeah, I found it in this paper. Maybe there are earlier citations of this. I think the big message to put is it's not a replacement for the good old things, yeah, for the physics-based models that we have. Yeah, it's just, yeah, I would not, if I have just a single forward simulation to do, I would not train a pin or a deep O-net or whatsoever, and then do one query to it. Yeah, there must be really some extra task that we cannot do efficiently with classical methods. And a single forward evaluation we can. Yeah, for example, if you want to embed it in a bigger optimization loop, then the, let's say, extra cost for the offline or the pre-learning, yeah, must pay off. Or another way, if you have a lot of data, let's say real-world measurement data that you want to fit into your model, then you can't do it so easily in standard FEM, standard IGA. Then, let's say the extra ability that MLDL brings you comes as a benefit. And then, yeah, I mean, there is very much on MLDL. Here we are zooming only to physics-informed ones. And if you want to look in the literature, there are many different synonyms. So Reisi, this was kind of the first, or this was the rocket start of PINS. It's called it PINS, physics-informed neural networks. There are others calling it universal differential equations or physics-informed machine learning. Kaniadakis, physics-based deep learning. These are all synonyms for the same thing, I would say. There are marginal difference between that, but more or less they describe the same thing. And in a quite recent survey paper on physics-informed machine learning, there's a very nice, let's say, timeline showing you two things. The first thing is the PIN. Yeah, the PIN was around about 1990. The preprint came in 18, but the journal was published in 19. The PIN, kind of what we often mark as the rocket start of PINs, was actually not the very first one. Yeah, years back, in I think it was 1994, there was a paper describing also how to solve differential equations, ordinary differential equations, and partial differential equations with neural networks. And that paper, I will come back to that in a moment, had already some ideas which are, in my opinion, better than what is done in PINS. Only drawback, 1994, the computers were not that powerful. So the concept was there, the compute power wasn't. So they could demonstrate some simple 1D, 2D cases, but of course it was not so impressive. And then it kind of, slept for some years until it was, in some sense rediscovered and marketed very aggressively, let's say, or very professionally, I should say that. You are not recording this, I guess. And then, this is what I meant. Basically, after this rocket launch, every second day there was a PIN paper. Some had PIN in the name. What were the differences? Some had a distributed PIN, others had weighted pins. Then was the idea of combining pins with a weighting function, like in Galerkin FEM. So all very nice, let's say, additions. Some were incremental, some were really, let's say, a big addition. Up to here. And I'm pretty sure this is not complete. There are more PIN. By the way, this is just the PIN concepts, not the millions of applications to problems. And then somewhere here, 2020, started a different, let's say, way of thinking with Lou, also from the group of Kaniadakis, about these deep O-nets, yeah? And that also triggered a second, let's say, wave of papers, kind of improvements in different ways, yeah? That Paris will talk about, I guess, in much more detail. But in some sense, the IGA nets are also here in this deep O-net family. Any questions so far? No. Then let's look at the 101 of machine learning, and let's start by just looking at the notation. Yeah, nothing too fancy. Yeah, scalar variables are just normal variables. We have functions. We have operators. Yeah, think of this as maybe the differential operator acting on a function, acting on a variable. Vectors are boldface. Matrices are boldface. That's it. We don't need more than that. Well, at some point we need tensors, but matrices into the third direction. ANN, artificial neural network. I'm also sure all of you have seen this before. Yeah, we have some input layer here. We have some output layer. We have some hidden intermediate layers. Then between the layers, there are the weights. These are basically rectangular matrices. And we can have the intermediate kind of values are numbered x, I, x1, x2, etc. So let's start at the very simplest thing. And why I do this is I want to show you that linear regression is actually also a very simple single layer network. And then activation functions is the first ingredient that makes it, let's say, more than linear regression. Okay, let's look at single layer networks. We have a couple of input layers here and one output layer. So a simple classifier, is it a cat plus one, or is it, sorry, minus one, or is it a dog plus one? Yeah, obviously this matrix is just, it combines it into one and kind of consumes, this is how I see it, n inputs, yeah, if this here is n. We can write it like this. If we have a couple of samples, that could be features from a picture, or that could be the picture, the pixel values just flattened, yeah. Each sample input corresponds to one label, yeah, so this would be maybe cat, dog, this is a Y2, cat, dog, etc. So, is this really so novel? No, I mean, this is just an overdetermined linear system. We could solve it basically since our, I don't know, second linear algebra lecture in the bachelor study. Or maybe third, I don't know, yeah. We can solve it, could solve it before deep learning became popular. Yeah, just pseudo inverse. Or if we want to do something more fancy, and okay, then we are maybe in the fourth or fifth linear algebra class, lasso regression. What is it? We are minimizing a least squares or this problem here. And we also impose the constraint. Yeah, so the lambda here is a kind of penalizing parameter. We do not want that the A matrix has too large values. Yeah, so otherwise, maybe it could be that this gives you, all the values are in the order of 1, and there's one outlier in the order of 20 million. If that is so desirable, I don't know, yeah? And this lasso would kind of penalize such a curing of extremely large values. Large in both directions, also large negative. Okay, so if we are now piecing two of these things together, yeah, so basically this green and red is our single layer neural network from before, and we just think, well, we are smart, we are adding one intermediate layer, yeah, which kind of comes from the input, blows it up, yeah, to more intermediate variables, and then kind of consumes it again. Does this help? It looks more impressive, yeah, we have a two-layer, kind of a multi-layer network. Does it help? Who says yes? Anyone else saying yes? It depends. Okay, I deduce from that you're a mathematician. We always say it depends, followed by a maybe. Okay, it depends. Unfortunately, it depends not, because when we write it exactly like this, yeah, so this is what happens from the input to the first intermediate layer. This happens from the first intermediate to the output. This is just a matrix times a matrix times this. Yeah, so A2, A1 are the given things, the weights kind of given in the evaluation kind of. And then X and Y, we can just replace it. This is a matrix. We can just replace it by another matrix thing. So we have found a very excessive representation of a single matrix. So conceptually, it's not giving us more. And the problem is, each single layer in a deep neuron or in a neural network is just, we leave bias at the moment. So the plus B shift, put that to 0. It's just a linear operation. So we could have 20 of these layers. They all could be consumed into a single matrix. So it only gives us something, and this is the depends. It gives us something if we break the linearity. We break the linearity by inserting activation functions, which, well, if they are just a path through, if they are just a input is equal to output, they are not helping. They have to be non-linear. So in some sense, they must make sure that this what is here, which chained, this is first input layer, output of that goes to the first activation function, that serves as input to the second layer, goes to maybe a second activation function, that this cannot be written as 1f A2 times A1x. Okay, activation functions, I said this one, the linear one, doesn't help, but sometimes and very often at the very last layer, you don't want to do something. Yeah, you really want the last layer to go out, let's say, linearly or modified. But for the rest, you have activation functions like the step function, this one, or logistic kind of soft step, which has rounded corners, hyperbolic tangent, ReLU, I think maybe the most used. Maybe not for good reasons, but most used one. It's not differentiable at 0, but okay, that one. And basically all of this can be tuned. Yeah, you can offset it. For example, the binary step doesn't have to have the step at 0. It can have the step at a parameter you prescribe. Or this one can also be scaled that it's not limiting to +1, -1. It can also go to plus alpha, minus alpha, or even plus alpha minus beta. Yeah, so these are just the vanilla or the textbook versions of that. You can, I think, in PyTorch or TensorFlow, tune them or write your own activation functions. Yeah, and I don't have this on the slides, but this is a, let's say, not a common practice, but becomes more and more popular, that you're putting your activation function to reflect your physics. For example, if you have a concentration, the concentration can be between 0 and 1. If you would put the hyperbolic tangent as the output, half of the output is wrong because a negative concentration doesn't make sense. All of these others don't make sense. Yeah, so you could kind of rescale your tangent hyperbolicus that it is centered around 1/2 and then goes to +1 and 0. Yeah, so you can see it as a kind of bandwidth limiter. Or another trend, and I'm also not going into detail, that you have learnable parameters in your activation function. That, for example, let's say that you say this point where you put the step is not a hard-coded 0 or a hard-coded 1, but you call it an alpha, which you also make a learnable parameter. If you don't know where the good, let's say, offset is. That is, and in that sense, these activation functions are no longer black box things that kind of are problem agnostic, but the more you know about the problem, your physics, whatever, the more you can invest thinking about what are good activation functions, what's a good network design. Okay, enough on activation functions, I guess. Yeah, so we are applying them element-wise. That means from now on, if I have A, that's the matrix, the weights basically, X, this is the collection of inputs. If I apply F here, I mean I do it element-wise. Okay, nonlinear optimization. So I feel a little bit ashamed because Sebastian talked about nonlinear optimization extensively in all the details. Yeah, this is just the simple nonlinear optimization that we have to do in ANNs. Yeah, again, this two-level neural network, we have the A1 and the A2 parameters, which we want to, well, we want to find the optimal values so that this loss function or this target function, objective function is minimized. So let's have a look at what it is. This here is just the neural network. Yeah, we have an input. Let's say the Lth out of S inputs. We apply the first weight, first activation function, second weight, matrix, second activation function, and then we literally compare it to the label, to the Lth label, and we want that this in the mean square summed up over all the inputs is minimized. Yeah, nothing too spectacular. And here, very often in the deep learning or in the machine learning community, all things are hyped as new. Basically, automatic differentiation, what we will talk about, or algorithmic, we'll talk about, is an old hat. Grivank and others had worked on that, I think, a decade or 2 decades ago, yeah, for a joint-based optimization. But now all of a sudden, these things make sense and are kind of hyped as the new things. Yeah. So what do we need? We need to be able to solve this nonlinear optimization problem. And in the simplest case, what do we need? Yeah, a thing called backpropagation and another thing called stochastic gradient descent. Yeah, that's typically the starting point of all the PyTorch or TensorFlow tutorials. Okay, let me try to explain backpropagation, which is just a fancy name for you apply automatically the chain rule until you end where you want to end. Yeah, so we have just one input, one hidden layer, one output. And yeah, you see, we call the hidden layer Z, that is F with the one weight alpha, A applied to the input. And that then serves as input to the second one. Yeah, so we have this simple chain G of F, etc., etc. Okay. Also, yeah, one of the first classes in, let's say, calculus, if we want to know what is the minimum or for which A and B does this mean squared error attain the minimum. Yeah, what we just do is we are differentiating this E, yeah, I'm now calling this thing E, with respect to all the parameters, set them equal to 0. And if we have, let's say, solved this, we know which A and which B we should put there. Assuming we have at the moment one output, one input. Yeah, that is at the moment the simplification we make. Okay, if we do that, and well, trust me, I checked this with Maple. This is, yeah, don't want to, do these type of errors in a presentation or in a lecture. Yeah, so some of these terms drop away. Yeah, if we work them out, we just end up here. Yeah, looks a little bit crowded, but not too difficult. Yeah, and we are now taking these two things. Yeah, so this one for DEDA, this one for DEDB. We just take this as, or the negative of that multiplied with some, let's say, scaling factor to update our weight. Here we are, A, and our weight B. Yeah, and again, this is standard iterative optimization. So now it's called learning rate. Before it was just called damping factor. Yeah, so new names make it more popular. Just an example, if we are now using, let's say, the tangent hyperbolicus for the first layer and nothing for the second one, yeah, just to show this is not magic. I mean, with all these PyTorch, etc. packages, in 5 minutes we can implement something and then it works. If it doesn't work, we have this idea, oh, it's black magic, why doesn't it work? Yeah, it's all math. You can do this all by hand or Maple or from Alpha to see, yeah, what it should give you. And if it doesn't work, you can verify, yeah, why doesn't it give me what it should? Okay, but we are not there, because I said the simplification and maybe the oversimplification was one input, one output. That's of course not learning from big data. Yeah, so in practice we have many of these. And also very often we don't have just one input, one output. So even in a classifier, we have many inputs, one output. And in regression, we have many inputs, many outputs. So what could we do? Yeah, that would be the picture, for example. Yeah, this is what we have to do. We have to solve such an optimization problem. Yeah, we have to calculate the gradient or the first derivative with respect to all the weights that there are, technically for all the input-output pairs. Yeah, so if you count here what this is, I think already all the weights give you something like 200. I mean, we can calculate it, but I think it was something like 200. Yeah, times the number of input-output pairs. So very quickly, this innocent-looking thing becomes, yeah, very, very heavy. And that's the idea of the stochastic ideas. Yeah, so gradient descent. Yeah, this one was just gradient descent. Stochastic gradient descent is, well, we are computing all this, but just for one randomly chosen pair. Yeah, that's the textbook or vanilla version. You can also say, I do it for a couple of randomly chosen. Yeah, it's a trade-off. One is maybe too little, all is too much, something in between. Yeah, a couple randomly chosen. Yeah, and then we are, you see, this is exactly the same formula as before. Yeah, exactly the same formula as this. Now just written in vector notation, and then here, yeah, for one, for the kth one, you could also have it over a couple. Okay, backpropagation explained. So I think we can, in view of time, skip this. What have we achieved? We know what an activation function is, backpropagation is, what SGD, stochastic gradient is. In practice, of course, there is much more or much better ones. Yeah, so let's maybe start here. You might use stochastic gradient descent or root mean square proportional. I have a slide on that. ADAM, I think ADAM is one of the more widely used ones in machine learning, or the BFGS, kind of Newton-like one. And also another remark, of course, doing this chain rule repeatedly, we are not doing this by hand. Yeah, that is where algorithmic differentiation comes into play. And I also have some slides explaining what AD, actually how it works under the hood. I do that because I want you to understand that it's not black magic, and how costly it is, that you are not kind of blindly saying, I can differentiate the world towards the universe or with respect to the universe. No, everything you do costs. And you see how quickly the costs grow. And then maybe you think twice, do I really need all that, or can I be more, let's say, selective? Okay, and I mentioned the biases already. Yeah, so without the B, we are only able to, let's say, map a zero input to a zero output. Yeah, matrix times a zero vector always gives a zero. The plus B, the bias, is kind of an offset. Yeah, sometimes, quite often, we want that. And yeah, now comes the mathematician in me. I don't want to care about all these details, and I want to make it a little bit more lightweight for you. All that, no matter how many layers we have, I call capital W, all the weights, kind of all the tuning things. And also, no matter how deep the network is, it's a calligraphic N. Okay, a few slightly more advanced optimizers. Yeah, so I think the next one you will find in PyTorch TensorFlow tutorials is RMS-prop. Well, what this here is really the vanilla gradient descent. Yeah, you are calculating the gradients, you have a learning rate. Here you're calculating the gradients of your loss function with respect to the weights, and you're updating that. So what RMS prop does, it has in addition a moving average, and it is calculating a kind of moving average from the last and the current one, or well, it's updating the current one with an average of this, yeah, so the gradient squared in a dot product way, yeah, because this is a scalar value, yeah, so kind of G times G transposed, or the other way around, depending on how you store the gradient. And then you have an average between that, a moving average between that and the previous moving average. Yeah, you kind of put some history dependent value, you could say, into it. And then, yeah, instead of having the learning rate times the gradient, you adapt, and that is all what the name says. You're adapting the learning rate depending on your moving average. Nothing more than that. And this brings already a lot of benefits because, well, fixing a learning rate is something you have to do yourself. If you fix it the wrong way, it either doesn't converge or converges too slowly. If you fix it, if you set it here slightly wrong, well, there is a mechanism that maybe makes it smaller if you chose it too large. If you chose it too small, it makes it larger. Yeah, so it is kind of an a posteriori mechanism to update adaptively your learning rate. Okay, ADAM, yeah, sounds like a name, but actually stands for adaptive moments. And I'm very happy that Sebastian introduced moments just in the lecture before, because this is exactly what we do. Yeah, we have, again, the gradient computation routine. We have parameters for moving averages, yeah, for the past gradients, and that's beta 1, and the moving average for the past squared gradients, a kind of this term. Again, this is G transpose times G, becoming a scalar. And then after computing the gradient, we calculate the moments of the gradient and of the gradient squared, update them. Yeah, so here are the learning rates that we specified, and then we are updating the weights from these so computed moments. Yeah, and this is, I'm not saying that you can blindly choose the parameters, but the more, let's say, automatism is in the method, the likelier it is if you choose a slightly wrong parameter, it still works. Maybe not optimally, maybe it still converges too slowly, but they are a little bit more forgiving, let's say. Any questions on this so far? Well, I'm not talking about BGF, the Newton-based one, because that A takes a little bit more space, more time to explain, and also that is, let's say, so standard in numerical methods, a kind of a matrix-free Newton-based solver that I skipped this year. And I would like to address the second thing, algorithmic differentiation. And I know many people call it AD automatic differentiation. Yeah, it kind of is true. It does it automatically for you. But yeah, it's not magic. It is just pure math, let's say. Therefore, I prefer, and I think in the original papers from Griewang and Walter and Naumann, it was really called algorithmic differentiation. So assume we have the following. We have two inputs, x and y, three outputs, f of that, g of that, h of that. And I'm intentionally putting it like this. This has, well, when Griewang and Walter introduced this, had nothing to do with machine learning. It was just, you had a couple of variables. You had f, maybe goal functionals, and you wanted to calculate the gradient of that with respect to the input. And that's exactly what the forward mode AD does. Yeah, so it calculates the derivative of all the three outputs with respect to one input. Yeah, so if you would want to know how do F sensitivity analysis, how do F, G, and H behave if I would change, let's say, the X could be the temperature of a system that has two parameters, use forward mode AD. If, on the other hand, you're interested on, well, how does one quantity of interest, one output, change with respect to all inputs, don't use that, because you have to do it, let's say, this one for X, throw away 2, third, yeah, you throw away 2, keep 1. You have to do it for X, throw away 2, 1. You do a lot of computations and throw away, yeah, most of it, the larger part of it. Yeah, then use reverse mode AD, because that gives you exactly what you need for one output, for one function, the derivative with respect to all its inputs. Yeah, and this AD, there are a couple of tools. Basically, I think these guys, Grivank, Walter, and Walter had some source code transformation. So you give in the source code, and then they kind of overwrite wherever needed the simple calculation by calculation plus its derivatives. There are also, if you have languages with operator overloading, C++, more modern Fortran, there are tools that do it by operator overloading. Yeah, so when you say, I want to do a plus, it overloads the plus by the plus in the data and the plus in the derivatives. I have some examples on that on the next slides. Okay, one thing, and we first look at the forward mode AD, is we interpret the entire computer program as a sequence of variables. Yeah, so, or the print statements, let's ignore them. But what basically happens, we start with some value, assign it to a variable, or at least we can think of, we assign it to a variable. Then we do something with this variable, assign it to another one, etc., etc. So, in other words, we can say the ith line or the ith meaningful instruction depends on all the previous ones. Yeah. Very often we have things like a loop, yeah, going from 1 to 20, or we have things, yeah, in at least in C++, these plus equal or minus equal operator, you're kind of overwriting one, something like this. This doesn't work, so we have to replace this by auxiliary variables. Yeah, kind of don't modify data in place. I'm not sure, have you ever worked with PyTorch and tried to, let's say, access a simple entry of a tensor and then differentiate that? I'm not exactly sure how it says it, because I always use the C++ API, but bottom line is it tells you I can't differentiate an in-place modified tensor, because, yeah, you do exactly this. And what you would have to do is take this tensor, modify it, and assign it to a new tensor. And this new tensor you can differentiate. So let's think of this as a, well, who of you knows what a tape is? Okay, some of you, it's this tape, something that, like a recorder. Yeah, where you kind of record sequentially, linearly, all what happens. Yeah, so assume that all the variables of your program have been taped, have been written to a tape. Yeah, and then if you're at some point, you have all of them, let's say, in a nice order. Okay, then we are still at forward mode. If we apply this chain rule, so the thing that I did by hand, yeah, so if we have the chain rule and we want to know what is the derivative of this ith variable with respect to all the others, yeah, or one of the others, we can simply write it like this. Yeah, it's a excessive application of the chain rule. And what we now introduce is a new way of writing this, dvi differentiated with respect to dvj, yeah, with a dot here. It's just replacing this and this one by this new notation. Okay. Why am I doing this? Because I want to illustrate how forward mode works. I'm more using PyTorch, so there it's really a seed. I'm not sure how it works. 100% sure how it, if you also call it seed in TensorFlow. Yeah, what you do is you really, the variable that you want to compute. Yeah, let's go back. What is this here? This is by definition, yeah, the derivative of vi with respect to vj. we are seeding the first variable. Yeah, so numbering is from bottom to top. We are seeding this with a 1. Yeah, that in some sense says, I want to compute the derivative of all the outputs with respect to that variable. If we would want to do it with respect to the third, we would seed V3. And then, yeah, we basically go, I have to go back and forth. We go through this sum here. Yeah. This is what V2 would give us, what V3 gives us, V4. Yeah. So you see the sum is going up and up and up. And then this is df with respect to dx. And if you see, yeah, so this is kind of the graph. It's not a network, yeah, it's really the computational graph of your forward evaluation. Seeding one variable has influence on two, namely on V2 because of this and V3 because of this. Yeah, so then V2 has influence on V3 and V4, and V3 has influence on that. Yeah, so you see it is kind of propagating and broadening towards the output. Yeah, and that is exactly, we seed one input and get the derivative of all the outputs because we are propagating to all the outputs with respect to that variable. Of course, if you would have two completely disjunct compute graphs, yeah, so if there would be an F4 which depends on an, let's say, X20 and not at all on any other ones, then it's disjunct. Yeah, then it's not giving you all the outputs, or basically this derivative of the F4 with respect to X1 is 0 because there is no path. Okay, I have a mini example which is taken from this book, yeah, from Martins and Ning. By the way, it's an excellent book. I would say it's on design optimization, really written as a self-study textbook. Yeah, what it does is this: we are seeding X1, yeah, and then it all goes to here. And this is what I meant. If, let's say, our real code says compute V1 equal to X1, then apply the sign, then here the product, etc. Yeah, so in this case, the sign would be overloaded by compute the sign and its derivative. The plus would be overloaded by compute the plus and its derivative. Yeah, the multiply would be overloaded by, you guess. Yeah, and you can do that either on the fly. So if you say, whatever comes now, my next 500 lines of code should be differentiated in forward mode, you kind of turn the tape on and it is recording basically everything on the fly. And then when you say, no, I need the derivative, yeah, you just kind of piece together what you recorded, always the second line per box. Or you can say, well, I just do my forward calculations and then I say, now I need the derivative. Then it's only doing the derivatives. Yeah, both is possible. Questions on that? Then let's look at the reverse mode, and surprisingly, forward mode is much simpler, but reverse mode is the one that is used in neural networks. Because, well, typically we want to know the derivative of the output with respect to all the weights. Yeah, a couple of outputs, million of weights. So reverse mode should be the more widely used one. But this here is if you just want gradients. Yeah, if you want to calculate your, say you have a function and you want to calculate the gradient or the Jacobian of this function for, I don't know, a stabilization in CFD. Yeah, very often you have something related to the Jacobian. You can algorithmically calculate this. Okay, reverse mode, we do more or less the same, only that now we have to look from reverse. Yeah, so in other words, this dvi, dvj now not has an increasing, but a, yeah, kind of, yeah, not decreasing, but a sum that becomes smaller and smaller. The more we go, the more we increase j. Yeah, and again, we do the same. We're introducing some helper variable now with a bar. So we can just write this here in a simpler way or in a more compact way. Okay, same scenario, and let's first look on the right. What we do is we seed which output do we want to differentiate with respect to all the inputs. And then, before it was, we started here and propagated to the output. Now we do it the opposite, in the opposite direction. Yeah, and same game, kind of. Yeah, we see it here, the V4, this out. Why is it 4? Should be 3. We see the we see the last one, the one that we want. No. It is 4, it is the 4th layer, and yeah, it is the 3rd variable in the 4th layer, sorry. Yeah, and then we are kind of going back. You see the sums get larger and larger the more we go to the input. And then we can compute kind of df with respect to all x's. Question to you, is this as simple as forward mode? I mean, forward mode, let me just go there, was simply we on the spot decide, I want to evaluate my function, and I would also like to have the gradient of this function with respect to x1. Yeah, that I could decide on the spot. I could kind of turn on the tape, run it, stop the tape, gather the gradient. Well, if I ask like this, then of course not. We need 2 runs. Yeah, we kind of first have to do the forward because, we need the values of a forward evaluation. Here we really have to write it to a tape. Yeah, or sometimes this tape doesn't have to be a file. Yeah, it can also be a piece of memory. Yeah, we have to do the forward pass that is creating the so-called computational graph. Yeah, kind of here. Here. Yeah, same example with the sign, product plus, etc. And once we have stored these values, then we do, and this is now basically the same, we are seeding, in this case it's V7, and then go down. Yeah, you see the sums get sometimes larger, and the values, these are now concrete values for this example. Then we are kind of collecting all the pre-recorded from the forward pass data. For example, where do we have it? For example here, if you see here, this one, it uses bar values. So where are we? Here, bar values, but it also uses values, just the function values from the forward pass. That's why we need the forward pass, that we can then collect them here in the kind of fusing together step. Yeah, so reverse mode is the more expensive one. But obviously for machine learning or for deep networks, of course, the more favorable one, because what do we have to do? If we have 2 outputs and 1 million of inputs, well, no, I shouldn't say inputs. If we have 2 outputs and 1 million of weights, that we want to optimize, we just need 2 reverse mode calculations, and then we get all the derivatives with respect to all the weights. Whereas if we would do it one by one, in this way, we would have to do for the first weight, and then we get with respect to the 2 output. For the second weight, for the 2 output. For the 7 millionth weight, so you see it's expensive. But, and please apologize if I'm, let's say, discussing this too much in detail, but I see, and I think, I'm not sure who was it you or was it Gianluigi who said, basically, we developed something nice, and then it didn't fit on the computer that was in the company. I think it was Gianluigi, right? Yeah. So, and this is, you can do that, but this calculation creates a very huge tape or computational graph or however you want to call it. Do you have a question?
Yeah, so we use so do you use a forward mode in pins? Because then you need the gradient of the neural network with respect to 3 inputs, but that gradient is yeah, let's say X, Y, and X. So you would run it 3 times, but then it would work if you have more than 1 variables, for example, that you are modeling with the neural network.
Yeah, so I don't have to repeat the question. Thanks for that. That's a very good question because I want to go in that direction. How expensive are pins, despite the fact that they are simply to implement? You need for the training step even both modes because you want to calculate, maybe I can. Yeah, so what the pin very simply does is it has, let's say, X, Y as inputs. It's producing, so the network is producing, a network of X, Y is producing a U of X, Y. And then in the loss function, let's take Poisson's equation. Yeah, so your loss function would be, I have the second derivative of U plus the second derivative of Y minus F, for example. Yeah, squared plus boundary conditions. So assuming we have already trained the network, yeah, so all the weights are fixed, each simple forward evaluation, well, unless we just are interested in the solution. But if we want to check, does this new X star, Y star, yeah, does this satisfy the residual pointwise? We have to do forward mode AD, yeah, even twice. Yeah, we need the second derivative. And if you have more complex, think of Navier-Stokes. You have not just U, but you have U, V, and P, and what have you. But you can do that with forward mode. But, and that is the thing that is very often, yeah, either neglected or not really seen. If you want to train that, you first have to do forward mode to get, let's say, XX. And then, because you are still interested in the weights, you have to kind of differentiate this tape already, or think of it as a compute graph. You create a compute graph for UXX, which you then reverse differentiate with respect to the 7 million weights. Yeah, so it works, and surprisingly, it works without, well, you can do many faults in the implementation, and so Deep XDE and all these packages do a great job to hide all the implementation details from you, so it works, but there is a huge computational effort involved. But thanks for the question. It's perfectly highlighting what reverse mode and forward mode, what makes the difference. Any other questions? So if not, let's move on. Yeah, these pictures are all taken from this book. This kind of illustrates from the mathematical point of view what this forward mode, reverse mode differentiation does. So these are kind of the dependencies from the inputs to the outputs. Yeah, and you see in forward mode, where did we start? Well, we started by seeding the first layer, V1, and then we kind of get this. Yeah, and well, mathematicians, this is just forward substitution. Yeah, so we can explicitly calculate, yeah, V1 dot is 1 times V1 dot. Yeah, we can calculate all this by forward substitution. Yeah, whereas in reverse mode, the dependency is more here. We started at the very end, seeded that, and then do a backward or a back substitution. Why am I putting this on? Because this, and it's a very crowded picture, but in some sense, it tells you when to use what. Yeah, so again, this was forward mode. We start, for the online people, I should use the pointer. Yeah, so we start here in forward mode and then go all the way down. In reverse mode, we start here and go all the way up. Yeah, when? So which is cheaper when? Obviously, if NX, so the inputs are much smaller or are smaller than the outputs, do forward. If the inputs are much larger, so translate inputs to the weights of your network, for example, are much larger than the functions that you want to differentiate, use the reverse mode. Okay, so time is flying, but I think we make it. Now we understand, I guess, all the 101 of machine learning. Let's put the physics into it. And I try to explain with this, let's say, very high-level slide, what is the difference between data learning and physics-informed learning. So let's first look on the left column or the left part. So what we are learning from in blue is just the data. That means we have labels. We have an input and the input is labeled. It's a cat, it's a dog, or it's whatever. Yeah, we let the network predict some, let's say, network label. Then we are comparing, is the predicted label equal to the right, so to the ground truth. Yeah, and then we are calculating the gradient with respect to all the weights. And yeah, this is just gradient descent, but yeah, you can replace this by Adam and whatever. Yeah, we are updating it until it converges. What we do in physics informed or physics based one is we do not have labels, yeah, but we have a kind of self-explaining label, you could say. Yeah, so here a human has to say it's a cat, it's a dog, looking at two pictures. Here you say, I know, for example, if I have Poisson, yeah, so the function, the solution that comes out, if I differentiate it twice, it should be equal to my right-hand side or to my load vector. Yeah, you can check if this is true by just taking the gradient, the residual of that. That should be 0, pointwise 0. If it's not, you know it's wrong. If it's slightly off, you know it's not totally wrong, but you have to still improve. Yeah, so you let your network predict based on the input, predict the solution. You are feeding this solution into your differential operator. Yeah, kind of, this is exactly this. You're differentiating the network twice with respect to x, with respect to y, and then subtract the f, and that's it. So some people try to classify this as this is supervised learning, this is unsupervised, yeah, because you don't need any pre-labels. One can even, yeah, I think this distinction is okay. One can even combine it. Yeah, one can say, well, I basically rely on the residual, but I have a couple of experimental or simulation data. Why not mix the two? Yeah, so I'm training mostly on physics, but I also augment it by some data that I have from experiments. Yeah, sometimes helps to speed up the convergence or helps to input real-world data into your process. And the whole thing why this works is this very nice and very old theorem, the universal approximation theorem, which, yeah, a little bit sloppy, says for every continuous function f from Rn to Rm, there exists an artificial neural network that approximates it with a given accuracy. In other words, if you say, I want 10 to the minus 12, this theorem guarantees you there is an A and N that does this function approximation. Problem? Well, general problem of mathematicians, we always have existence proof that don't tell you anything about how to find it. We just say it exists. It doesn't tell you if this is maybe a 20 or a 20 million deep neural network and how to find the optimal weights. It just says it exists. But okay, that's better than nothing. We are not chasing behind some unicorn. We are chasing behind some existing ANN. Okay, this is a very simple example. Yeah, Poisson equation now even in 1D. And this is how the PIN framework, and I said before, there was an earlier version that did some things differently and I think better. this is what pins do. Yeah, you say I have the second derivative of u on the right-hand side. I have, let's say, Dirichlet conditions on the left and right. I just put this as, yeah, so this is literally, we take the network, differentiate it twice with respect to x, compare it to f, and the second thing that should be satisfied for an x that is at the boundary, yeah, the network, read this as the solution should satisfy the boundary condition. Yeah, and then, yeah, of course, this is the textbook version. In practice, you have, let's say, scaling factors, which are difficult to find and all that. Point is, in the, let's say, pre-pin work, they used a simple trick which is called Dirichlet lift. Yeah, so who knows the word Dirichlet lift? Okay, quite some. Yeah, so if you say, oops, if you have your solution, yeah, and that applies to finite elements, whatever, yeah, classical numerics. If you have your solution, you write it as a solution that satisfies your Dirichlet value plus a solution, kind of the homogeneous one, that is 0 at the boundary. Yeah, and then this is, let's say, if you want that your solution, let's say, looks like this, yeah, would be maybe 1 here, then this UD is 1 there and goes very quickly down to 0. And your U homogeneous satisfies homogeneous Dirichlet conditions. Yeah, kind of does this. Yeah, and if you superimpose the two, you get it. Nice thing about this is here, yeah, it's very hard that you say in one point at any cost, I want that the Dirichlet condition is satisfied. You can penalize it like hell, but that doesn't make it simple or easier to train. Yeah, with this, it can't do other than satisfying it because you say, I'm not predicting at the Dirichlet, at the boundary, I impose it. Yeah, imposing is stronger than, let's say, penalizing. But okay, small detail. Yeah, and wow, this is exactly what I said, history, yeah, 1994 and then 98. Well, I think Lagares was the paper I was referring to, where they really call it neural networks for differential equations. And yeah, they implemented this with this Dirichlet lift. And then, yeah, Moonshot, Raisi et al. Labeled it physics-informed neural networks. And then the journey began. Here are a couple of, by the way, not sure, so nearly everything is kind of linked. The papers are linked. If you have the PDF version, the papers are linked. At the end, there are some 20 or 15 pages of references. You can jump to that. And here you can also jump to the GitHub or NVIDIA repositories. They are all, I think, NeuroDiff is for Julia, NeuroPDE for sure is Julia. This is Python, this is Python. I think also this one. Okay, a few examples because I think that Paris will talk much more in detail about this. This is from, yeah, basically one of the earlier papers. Yeah, so they first started with something like Poisson, etc., and then this is Euler, yeah, Euler flow, already a vector value or a system PDE, which is not that easy to solve because, yeah, you see in Euler flow you can have sharp discontinuities, yeah, shocks, and if you just do it, let's say the simplest way, yeah, so these are the training points, you put them in the domain where you want to satisfy the residual and on the boundary where you want to satisfy the boundary conditions, you get a kind of smeared shock. Yeah, very similar what you get with, let's say, SUPG if you have a too high stabilization parameter in finite elements. In this paper particularly, they invented this adaptive sampling. Wow, but it is basically you identify where the error, where this here is particularly large, and pump in sampling points there. Yeah, and it gives you a somewhat better shock resolution. Another one, and this is really just a collection of a few examples. This is more recent, to show the, let's say the spectrum of what pins can or at least have been used for. So this is learning turbulence models. So this red one, DNS, direct numerical simulation, the most honest thing you can do and the most expensive. And then two different pins here, which have been trained to reproduce the quality of a DNS. And well, it looks quite okayish, I would say. Another one I like very much. So it's kind of show me your cup of coffee and I tell you what's the flow field. No, what they did is the following. They took a lot of BOS, background-oriented Schlieren images. What is basically done, you have a background which has some patterns, some random pattern, and then you put a lot of cameras around your, meanwhile, cup with cold coffee, and then you get a lot of snapshots. And they did it, I think they did it with a, let's say, either with an experiment or with forward simulations. They knew how the flow field really looks like and what the picture that, or the sequence of pictures that they do corresponding to this flow field look like. And then, after they had trained the pin with that, they said, I just make a picture and I can then tell you what is the velocity, what is the pressure. Kind of fancy, I would say, maybe not for coffee, but for other, let's say, industrial applications, useful thing. From a BOS picture, you get a qualitatively okayish insight into the entire flow.
I have a question.
Let's try it like this then.
Yes. Thanks. I have a question for the previous slide, actually. Do we have any comparison on the computational times for the three models? So how much time does the direct simulations and the training took for the same accuracy? Thanks.
To answer your question, thanks for it. First of all, I think there are some computational times in the paper, but I don't know them by heart. So, do you know? Okay.
May I come up with a different version of the question or interpretation of myself? So you need to evaluate the residual. So that means you can nicely compare that with an iterative solver, right? Which essentially, or a matrix-free solver, which essentially has the same effort. So that means if you need 100 iterations of an iterative solver, then at the same, 100 iterations of this one will be, let's say, roughly the same costs. Would you agree? Yeah. So that gives you an estimate, right? If you know the number of calls you need, and then you can compare with the iterative solver, and then you can make a guess what is possibly more efficient.
And exactly. And you mentioned the thing, and this is which I like. You measure not the error, you measure the residual. That's the same thing in numerical methods. People often say, well, I bring down my residual to 10 to the minus 15. I'm solving the problem. No, maybe you're solving a completely crappy problem very exactly. You are not residual 10 to the minus 15 doesn't mean you've solved or you found the solution. You've just found a state which minimizes or brings the residual down to that. Could be, so especially here, there was some, I skipped that. There they, not sure how much familiar you are with gas dynamics. What they did here is they trained it for the conservative variables, density, momentum, total energy. These three fields looked okay. The velocity, I should write it down. So we have rho v, looks like the product of two variables, but actually it is the momentum. So normally you have rho, momentum, and total energy as the conservative variables. And then they plotted the velocity. The velocity, what is it? Velocity is kind of, you take your m, if you call it variable 1, variable 2, variable 3, they took variable 2 over variable 1. And it had a non-physical behavior. It should be something. Not going too deep into gas dynamics. And this is something it didn't have. Yeah, because, yeah, you train for 3 fields. This thing doesn't really understand physics. It's physics inspired or physics informed, but not a physics genius. Yeah, so it had some unphysical pattern in the velocity. And I think what they did then is added velocity as a 4th field to train. Yeah, then it also understood that the velocity should behave physically. Yeah, so why did I say it? Yeah, coming from this, if you bring down the residual to something, it doesn't mean you're solving the problem correctly. Okay. Yeah, and I'm pretty sure Paris will have more because they really worked. So the entire Brown group around Professor Kaniadakis in the US worked on this very successfully and very extensively. Very briefly, we have 8 minutes before the picture or the photo to be taken. Yeah. What are the strengths? They are very easy to implement. So I say any model. Technically, you can do any model, but yeah, be careful. Sometimes physics aren't your friend. Yeah, by just adding more MSE terms, you can augment it by simulation or experimental data. Yeah, that would be the supervised part that you add to it. It's also very easy, and remember in the beginning I said I wouldn't use this as a replacement for a simple forward evaluation. Yeah, but if there are some, let's say, parameters, temperature parameter, or something that you want to deduce, yeah, inverse modeling, you can make it an output, you can train for it, and then you can very easily get this, let's say, inverse parameter that you would otherwise have to very costly back calculate, get it for free, in quotes, as an extra output. Yeah? So for inverse modeling, it makes really sense, or the extra costs of training make really sense. It is super flexible. Yeah, so this looks like one monolithic network. Think of a network for the velocity components and the pressure. Think for one for the entire velocity and the pressure. Yeah, so basically this is how you can, I'm leaning towards saying you can produce new pin papers. No, you can really explore the flexibility, and if you find something that works very good, very well for a particular problem, publish it. There are also some weaknesses. Yeah. As I said, for a single problem instance, oh no, sorry. I should have read this more carefully. What you do is you're coding a single problem instance. Yeah. So exactly this with parameters. Yeah. The geometry, everything, boundary conditions, everything is hard coded in the loss function. That's basically my let's say motivation why we developed IGA nets. Yeah. Except for maybe some, let's say, problem parameters that you get otherwise via an inverse problem. They are poor in generalization. Yeah, so assume this. Yeah, let this be an ODE, and you are training it for, let's say, the first few seconds. This is the exact. This here is the exact physical behavior. You are training it, and it looks very good up to this point. And then you say, well, I just want to know in the long term, what does this trained model do in the long term? It can't know. Yeah, it can be very, very poor. Thing here, people very often kind of hit on pins because of that. They don't extrapolate, they are bad. Give me a finite element code that can extrapolate without calculating. Yeah, I mean, we see this always as a weakness. We should be happy that it can interpolate already, because in FEM, every new point would be a forward calculation. Yeah, so don't be too negative about that. Okay. Another thing, it gives you pointwise output, yeah, as we've seen here. That's how many million forward evaluations after having trained you need to get a complete flow field. Yeah, you only get points.
Excuse me, Professor Müller?
Yep. Yes.
I have a question. There is a way to improve the estimation of that solutions outside the training data?
Yeah and no. So thanks for the question. The way to improve it are at the moment deep O-nets. So it's a little bit black and white, but pins are considered, yeah, developed to their ends. They have limitations and you can't overcome them too much. So now the trend is deep O-nets, which do not have this generalization incapability. Yeah, so if you stay tuned, on the next few slides, I have also deep O-nets. Does that answer your question?
Thank you. Yes.
Okay. So we had this. Yeah, already high computational costs. We discussed it here with forward, backward, etc. I don't talk about this, but hyperparameter tuning, you don't believe how many attempts it needs to have a pin or an IGA-net, to be honest, say an ANN in general, set up in the right way, how many parameters, which activation functions, etc., etc. Yeah, so the thing I want to say is now, yeah, so let's skip this hint. I think I've stressed it more than enough. We are in a design optimization school. So the question is, how do we feed design if everything is hard-coded? And one thing we can do is parameterize pins. Yeah, so I hope you can see the color coding. Yeah, so I have now X and Y. So obviously we do 2D and have UVP, smells like Navier-Stokes or fluid flow. And we are adding 3 more inputs, alpha, beta, gamma, as design parameters. Of course, you can't put your entire mesh consisting of 1 million grid points there. Yeah, so 1 million and 3 inputs is maybe not the best thing to do, but 3 might be okay. And what we did with a master student who is now doing a PhD in Braunschweig, we kind of combined autoencoders with pins. So this is my slide on autoencoders, the long-awaited slide. But I mean, autoencoders aren't that super tricky either. Yeah. So you have an input front, you have an output front, you have a latent space. So it has kind of it becomes thinner and thinner and thinner until you have a very small dimensional latent space. And then in exactly the same way, but mirrored, it decodes it. And what you want is this network learns to map inputs literally to outputs. Yeah, so you basically leave all these connections, trainable parameters, and whenever there's an X, you want that Y is equal to X, either point-wise or in whatever measure. Yeah, so ideally it should not modify X to the output. Once you have done that, you throw away the, let's say, the narrowing down, the encoder, and you just take the decoder. Okay, what have we won? At the moment, not much, but remember this, no? This. Yeah? If we add just a few more inputs, we can have parameterized pins. And I think this is exactly what you also mentioned on one of your last slides. Yeah, we kind of make these Z extra inputs to the pin. And this is what we did together with Monolith AI, so a startup in the UK, London, I think. They are very much on engineering, AI for engineering applications. We literally took their encoder, decoder thing, which is really, it's closed source, we couldn't look into it, but it's really, let's say, state of the art, and combine it with a self-written pin. So, and we compared it to Phoenix, yeah, also a standard finite element package. Yeah. What you see here is the collocation points, yeah, on which we sampled the pin, and the Phoenix mesh. Yeah, so it was a triangular mesh. I've not drawn the triangles, but you see the grid points of this triangular, piecewise linear triangular mesh. Yeah, and very many around the, let's say, the border or the boundary of it. Just 1 or 2 more minutes, then we are done. Yeah, and now the question to you. So we trained it all fine. Which is which? So we have the velocity magnitude at the top and the pressure at the bottom. We have a NACA. Yeah, NACA is a way to describe airfalls. We have 5-degree angle of attack. Yeah, so the flow is not coming completely upstream, but a little bit from here. Which is which? Which is Phoenix? Which is our AI pin? Don't tell me I made a copy-paste error. These are I can show you the LaTeX source code. It's really 2 different figures, or 4 different figures. You can tell, right? Oh, you can tell. No. That is the big problem, the boundary. Let's say, I come back to that in a second. Let me first have the nice thing and then tell about the truth. Yeah, left is pin, right is phoenix. And I want to show you a video. Yeah, so we have alpha is with an F, unfortunately, is the angle of attack. And then we have 3 latent space variables. They have nothing to do with the 3 values of the NACA. Yeah, so NACA is a little bit a fake example, but mathematicians can do that. Yeah, we have encoded a lot of simulations or pins, and now we can play with these latent space variables and get qualitatively okayish solution fields. And what you were asking, is it accurate at the boundary? No, we did drag and lift coefficient calculation. They are horrible. Yeah, of course. I mean, even though we had a lot of points on the boundary, we just have points. But drag and lift are integral values. Yeah, if a single point is, not accurate, it ruins everything. And that is, and I come to that. I can't overemphasize IGA nets. This removes all the troubles that we have with pointwise pins, because this is a kind of pin in a nice mesh-based or IGA-based framework. But I think we should stop here. Now take the photo, and then this afternoon, Paris will talk about deep O nets, which where's the my lucky chance would have been exactly the last topic of my first part. Are there any questions? Yeah, you have a question.
First question, if you train a variational autoencoder on the geometry reconstruction and then you want to predict lift and drag, why use the pin? Couldn't you directly train a multi-layer perceptron to predict lift and drag from the latent space variables?
Yes. Oh. That would be exactly this output, what output you took, and then post-process it, but train what you are really. So the answer was, yeah. So in this case, don't learn for the output field and then post-process it, but learn immediately, so as outputs, drag and lift, or any other quantity of interest. But you indicated you had a second question.
Just to make a quick computation, in the case of the Poisson solver, if one wants to estimate the computational effort, is it correct to say that we have 4 derivatives, like the first with respect to x, the second, so 4 derivatives. So we would need 4 so how many forward and reverse mode auto differentiation we need? 4 reverse and 4 forward, something like that?
Yeah, you could say that, or because you first need to do, let's say, every x or y triggers a compute graph. Yeah, so this would be with respect to x, triggers a compute graph. And then you're differentiating this again. Yeah, kind of blows up this compute graph, but this is what you need to compute uxx. And then you would reverse mode differentiate this compute graph. So I would say you'd have 2 nested compute graphs forward mode generated, which you are then reverse mode differentiating with respect to the weights. But you can, of course, do it like second derivative is the derivative of the first derivative. But I think that is more expensive because then you need 4 reverse mode versus otherwise 2 bigger reverse mode. Other questions? Then, yeah, I think it's time for a photo.